All right. And so we're somewhere right around page 99. We're talking about statics. Let me see if my computer will share screen here someday. Oh, that's a email we don't need. Okay, so somewhere there. Now, we went over this last time a bit, but if you recall, I think we were going to try and talk about statics problems with circles in them, basically. So remember, here's your checklist. The couple of the big things: make sure you draw lots of pictures. You could choose some of Torque's about any pivot, and a lot of the problem is figuring out your angles and which pivot to choose for a particular problem, because one choice of pivot is often much easier than the rest. So that's what we're going to kind of focus on today, is this pivot drawing, but with circles in it. So let me see if I can get you a good problem here. By the way, I thought about this one. Whatever. Let's talk about this some other time. There we go. I don't think we talked about this one last time. I think we said we were going to start here. So let's look at 12.8, page, whoops, I just passed it, page 103. And then I'm going to make this bigger and just kind of draw on it right here. Can I make this even bigger? There we go. All right. So reading through this problem, you've got it in front of you. We know the radius of the ball. We know the length of the plank relative to the radius. We know where point B is. We know the masses, etc. Okay, so I think it even said we know the angle, but whatever. So in this case, let's talk about first the forces on the ball. So somebody tell me one force which is acting on the ball.
Normal force of the wall
Okay, and which way is that going to push?
to the right, which for the center of the circle.
Yep. I'll call that normal force A. All right. Any other forces?
Well, mg down from the ball.
Okay.
And then same thing for the rod.
Okay. I don't know which mg is which, so I'm just going to call them both mg. Normally we would label them. Does anybody know which is which? Which one was the plank? Sorry, I got to open my book again. I lost the page.
M2 is the plank.
Thank you. So that should be M2G, and that means this is M1G. All right. What else? What's another force?
The normal force of the plank on the ball.
Which way does that push?
Wouldn't it be towards the center of the ball?
Exactly. And so this is basically one of the tricks I wanted you to see. Notice the normal forces, whether you're on the plank or the ball, they tend to point directly towards the center of the ball. I like to think about it like this. If this ball is here, no matter what you do, any surface that touches the ball necessarily must be tangent to the ball. And that means the ball will always be pushing perpendicular to the surface. By Newton's third law, the surface is always pushing radially inwards. So that's one thing I wanted to get out of this FBD, was that these normal forces point radially inwards on the ball. Got it? Okay. Is there anything else? What holds the ball up?
Friction?
From the wall or the plank or both? What's your gut tell you?
Both.
Okay, so which way is friction at point A?
Would it be pointing up?
Yep. Friction A. And then how about at point B?
Pointing up to the left?
Yeah, towards the pivot.
Yeah.
Now, that's obviously on the ball. Which way do the forces act on the plank for part B?
Should just be the opposite, correct?
Yeah, there's
normal
going to be
force up
one.
2.
Yeah, so there's a normal force B on the plank, and this explains why we normally draw free body diagrams rather than to try everything on the same. Are there any other forces on the plank, or are we good?
That should be. Oh wait, is there a reaction force at the pivot?
Ah, good. I tried to get you. And I think in the solutions, I actually, instead of calling this Rx, I think I called it Cx and Cy. Just because I was calling points A, B, C. So this is a trick you could do. You could label the points, different points, and mention forces by name of the point. All right. All right. So far, so good. Now we can learn something about the ball by doing torques on it. And actually, let me clear this out. Let's go to the solution here where I have that same figure already drawn. What was that, 12.8? Somewhere. Sorry this is taking so long. Okay. There's our pictures. So far, so good. Now, in this case, I want to first consider the ball. Isn't this much easier to see when you do separate FBD, right? But in this case, I want to think about torques on the ball. What choice of pivot eliminates the most forces if I'm doing sum of torques on the ball? Which choice of pivot eliminates the most forces for a torque equation for the ball?
Would it be at FA and NA? Like that point? Like right there? Yeah.
How many does that eliminate?
3.
What's the third one?
Be also the M1G pointing down too, since it goes through all the way to the right, or does
Is-
that not work?
That line of action does not go through the pivot.
Got it.
So that is a bad choice because I claim you can get rid of 3 forces.
Is it the center of the circle?
Let's see. If we choose the center, obviously mg causes no torque. That one. You see it? So the idea here is we could have chosen the one Jesse chose and it would work. But the one I chose, or wait, Alonzo chose this one, is better. Because how many forces does that eliminate? 1, 2, 3. We don't have to worry about those. So notice the torque equation is easier if you choose the right pivot point. Also, you're going to see how much easier it is when we try to figure out the lever arm. What's the lever arm for each of those 2 forces? So here's the line of action. What's the lever arm for FA? What's the lever arm if the center is the pivot and the force is FA? Pirate says,
Just should be R then.
R. Me lever arm is our perp. Okay, now look at this other force. Notice that frictional force is tangent to the curve. What do you think this lever arm is?
R2. Well, the same R also.
Yeah, I gotcha. And so in this case, it's so easy to write the torque about the center of the sphere or cylinder. So that's the second thing I wanted you to get out of this. Number 1, normal forces point perpendicular. Number 2, if you use the center of the ball as the pivot point, not always do we want to do that, but sometimes that's really convenient because all the normal forces tend to drop out and mg drops out. So we can get a really quick relationship. And in fact, we see that R times FB must equal R times FA. And notice immediately the radius drops out. We see that the two frictions must be equal. So far, so good. If the two frictional forces weren't equal, the ball would rotate about its center. Cool. Does that imply the normal forces A and B are equal?
No.
Why not? I thought F equals mu static times the normal force. It's not rotating, so it's static. Shouldn't F equal, doesn't this equal mu static times normal force B?
But does the NB and NA have different values?
Yeah, but wouldn't this one over here equal mu static normal force A? And assuming the two coefficients of friction are the same, wouldn't they just drop out? Let me rephrase. In general, this is not necessarily true. Why not?
Would it be the orientation where the forces are?
Nope.
Hmm.
What has to be true for F to equal mu static N?
About to slip?
Did anything in the problem say it was about to slip? It said it wasn't slipping, but that doesn't mean the same thing as on the verge of slipping. So that's why I can't use these two equations here. It might be true, but it almost certainly isn't true. I don't know. So yeah, got that? That's a subtle point. Is everybody cool with that?
Yeah.
And then if we actually go in and do the force equations, notice here they are. So let's just look at the ball. Forget the plank. You could do the plank later. Notice you're going to have to do some angles, right? So this is a good problem to review later without having the solutions open and make sure you could reproduce this result. But what you've got to do is split this thing up, and you got to do a little bit of geometry to figure out the two different angles, right? Now, from the picture, I forget what theta was, but I think, let me see if I have it here. Geez, I lost the page again. 90 something. 103. Theta is the big angle. So I have a feeling that this angle up here is theta, and that this angle right there is theta, because we were told this big angle is theta, and those two look like the big angles. So you could go through and try and, whoa, geez, I just closed that book again. Oh my gosh, whatever. All right. So review this later. All right. Try it again at home without me doing it all with you, and see if you could reproduce this. And notice you get something for the plank as well. Now let's go back into here and make this a little smaller just so we can read this, see if there's anything else. Now, if you're curious and want to practice your geometry skills, I claim you could figure out this angle from this problem statement. So if you want to see if you know what you are doing, see if you could do that. It's tricky, but I think, well, I thought it was fun. So if you want to practice geometry, there you go. Now, the goal of this problem was literally to do the FBD and write the forces to practice seeing how these things relate to circles. I would like to do a couple more examples of it and just see the ways I might vary this type of problem and give you some mix-ups on how to do circles. So rather than beat this to death, unless you have a question, which I welcome, I'm going to move on to the next one. So that said, any questions before we move on? It was just practice writing the forces and torques. Let me see what's in the chat there. Oh, whoops, that's something else. Oh, what is that? It says more. Oh, breakout rooms. Maybe I should close those breakout rooms. All right, we'll do that. That way I stop getting that signal. Sorry about that. All right, let's keep going. Boy, these ones here. Did I talk to you about these already? We did a lot of problems on Monday like this one, right? So, yeah, there we go. Let's go to 12.11. You guys watch out for these. Make sure you do them. You can learn a lot in those problems. The different styles of lever arms versus RF sine theta. Okay, let's look at this one. I'm going to make this big again in a minute. You've got a wheelchair. The wheelchair is at rest against the curb, and this person can exert a force tangent to the top of each wheel of size F. Radius is this. Mass of the person in all of her essence is just this. So we know the mass of the wheelchair, person, everything they're carrying with them, all that. And now think about this. I hope you agree it seems logical that the mass is centered above the axle, right? They're sitting in this thing. Their legs are going to bring the center mass down, but most of their body is either going to bring it up. And so it shifts it up slightly. So it's not right at the center of the wheel anymore. Now, a good question might be, determine the maximum height allowable if a reasonable person can actually try to get over the curb. Obviously, you would try and build a ramp, but in some cases, maybe that's impractical, or maybe between ramps, you want to make sure someone could get up and down. And so maybe you could do a study on human beings and figure out what force they could actually reasonably hope to apply. And you might know, you could plug in radii of different wheelchairs. And so you could analyze this situation thoroughly for a large range of people and figure out a range of curb heights that might work out. So our goal is to figure a curb height that allows a typical person to roll over it. Obviously, if it was a millimeter high, the person could just roll right over it. So the question is, how high can we make it until they can just barely get over it? And that would be an important limit to understand for designing curbs. Now, let's make this bigger so we can draw on it. Okay, and can I make it one bigger? Oh, that's a little too big. Let's say 500. There we go. Okay, so now what is one force? Somebody give me one.
Could there be a normal force at the edge of the where H is?
Okay, okay. And yeah, which direction would that point?
Where's the center of the wheel?
Okay. Towards the center, and I'll just back it off. It's just, that's my attempt to draw that. So we'll say that's the normal force. What's another force you might face? And see if you could do this one. If you might be tempted to look at the solutions. See if you could do this without looking at the solutions. Then we'll all look at the solutions together, okay? And if you already looked, that doesn't offend me at all. Just whatever.
MG down from the center.
All right. I love that MG, right? There's an MG down from the center. What else? Oh, wait, that's not right, is it?
From the center of the X.
The center of mass. Ah, okay, let's undo that one. I'm going to try this other one. There it is. Hopefully you can see that. Sorry, I just screwed up that last one. All right, what next?
Wait, I have a question.
Yep.
So the normal force is going to the center of the wheelchair, or the center of the mass of the
Normal
wheelchair?
force goes towards the center of the wheel because it
Okay.
goes towards the center of the circle because, right? That's like the last
Yeah,
problem.
so it's orientating.
Yeah, so that's what's a little different about this one.
Okay.
That one should go right towards the center. Got it?
Mm-hmm.
Yep.
Could you count that point as kind of like a pivot point to make it like the R?
Which point?
Of the green arrow.
The tail of the green arrow?
Yeah, because I'm technically like pivoting across.
Yes. So this is the point about which this thing should rotate, right? Isn't this thing going to try and rotate over the curb?
Yes.
Yes, I agree. So it's going to try and rotate around the curb, and that's the pivot point. Absolutely. Okay. Other forces.
Another normal force
Where?
all the way in the bottom of the wheel going up.
Okay. Like that, maybe?
Yeah.
Okay. Are there going to be any frictional forces?
Bottom of the wheel and the corner.
Okay. Which way?
Uh, to the left, or the corner would be perpendicular to the green arrow.
Okay.
downwards.
I tell you what, before we do that, which way is the person pushing on the wheel? Which way is the person pushing on the wheel?
Pushing forward, or should be, yes, pushing forward.
Now, you could argue there's two of those, right?
Correct.
One for each hand. I'm just drawing it like that. And these arrows are not to scale. Sorry about that. They're all different sizes. But based off that, Denna, which way do you think friction is at this green point here?
Opposite, downwards.
So like that?
Yeah, like that.
No.
No.
It's going to go. Think about this. This person is trying to make the wheel rotate that way. The ground opposes that rotation and exerts a frictional force this way. Does that help?
Yeah.
All right. And then let me just label this one. This was mg. So which way do you think friction points at the bottom?
Forward.
And if you look at the solutions, I screwed it up too, Denna. So I got to fix that one. I noticed that earlier. But I'm going to, fortunately, I have a get out of jail free for my screw up, which I'll explain in just a minute. So we'll call this one friction 2, and this one we'll call normal force 2. All right. And I think that force up at the top was called F. And so you could argue whether you want to call it F or 2F, something like that. All right. So that's the direction of the forces. Again, part of this problem was figuring out, man, which way does this thing roll? Now, my claim is we actually drew too many forces. Whoops. That's not n squared. That's n subscript 2. We drew too many forces. Why? What is this wheelchair trying to do?
Barely lift off.
Lift off. What does that tell you?
The pink forces are to be crossed out.
Yes. These are negligible because this is to lift off. You're no longer touching the bottom. That normal force goes to 0. Got it? So let's go in there and look at the solution now. Which question was that? 1212?
12.11.
Oh, 1211. So you see what I screwed up down there? I'm a bad person. Ding, 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 ding. But fortunately, my screw up was 0, which is probably why I never noticed that I drew the arrow the wrong way. I was in a hurry. I'm like, this force doesn't matter anyway. Just stick an arrow on there. All right. So there's our FBD. Now, we already mentioned that this is a good pivot point. Why is that useful? Which forces are eliminated in the torque equation?
Just the normal and the frictional forces, correct?
Yep. Notice by thinking about torque, this actually becomes a 2-force problem. Isn't that cool? So even though torque in chapter 10 was very difficult, here's an instance where it's actually helping us out. It takes this nasty problem and helps us simplify this. All right. So sorry if my color coding didn't match perfectly. What technique do you think you would use for attacking this? Do you think you would use lever arms? Do you think you would use R vectors and R vector cross F vector? Do you think you'd use RF sine theta? Or do you think you'd use R force perpendicular? What do you think you would want to use here if I wanted to do a torque equation?
I would use RF sine theta.
Based off my reaction,
I'm guessing that's wrong.
no, it's correct. That's just not the fastest. I deliberately chose this one because I think if you look down here, wait, maybe. I think you see the lever arms pretty easily. Let me do it up here in this picture. I'm going to draw the lines of action for these forces, okay? That's the line of action for mg, right? It's a line through mg extending infinitely long in every direction. That's the line of action for the force 2F or F. And remember, we are calling this down here, whoops, let me get a, that's our pivot point right there. Right? So R perpendicular, give me a second. Is that, well, that's a little faint. R perpendicular is that distance. I don't like that one. Sorry. Let me undo that. I got the wrong marker here. That distance right there is R perpendicular for the mg force. At the same time, this vector, or this distance, is R perpendicular for the purple force, or F. We know some heights in the problem and distances already. To be clear, we know that this distance right here is h. What's the total distance all the way to the top?
2R or
2r. So do you agree we pretty much know R perpendicular right away? It's 2r minus h.
Yeah.
Now the other one's a little bit trickier, but we do know that this distance right here is radius r. I know that this distance right here is h. So what's this distance right here?
R minus H.
And then can't we figure out the lever arm from that? I should be able to figure out this distance because I know two sides of a right triangle. That's what I drew down here in the solutions. So that's what I was trying to show you there. All right. And once you get that, the rest of the problem is easy. mg R perpendicular for this one. Well, that's x. Well, that's this nonsense here. This one is 2f times its R perpendicular, which was 2r minus h. And then it's just working your way down and solving for it. And we get this weird result. And notice the result depends on the force to weight ratio. That's cool, whatever, in this weird way. Now, obviously, again, it's better to build a ramp, but there's probably some situations where maybe between ramps, you want to also make sure this works out. So you could do some research, look up a value of F, use a value of mg for a human being, and then just kind of get an idea and hopefully design a curve that is navigable for the vast majority of people that are in wheelchairs regardless, whether there's a ramp there or not. And that would be a cool thing to do. I don't know. Let me pause for a second. Let me see what's in the chat there. Perpendicular just means you've got a right angle. So again, let me go in there and just make sure I hammer that home. Well, let's do it on the whiteboard. Okay. Whoops, let me get me up here. That lever arm concept is kind of handy, I think. So again, let's say you have a pivot point and there's a force that you apply. If you want to draw a lever arm, the first thing you must draw is what? Got cut off there. What is it?
Line of action.
Draw the line of action. By definition, the lever arm says go from this point to that line and make a right angle. That's how you get a lever arm. Notice you get a right angle. Now, we use this so often, sometimes this line is called the perpendicular bisector. It hits the line of action and splits it into two equal points using a right angle. That's why it's called the perpendicular bisector. That's why it's got this special symbol, R perpendicular. You got it?
Yeah, I see it now. I like that visual.
Yes. And so if you look back at chapter 10, I drew this out in the 4 methods of torque, which is on some page, which I don't remember. Cool?
Yeah,
Yeah.
I'll look at it later.
All right. So let's try one more just to make sure we got it. Let's say this force was angled. I want to get the lever arm. What do? Gonzalo? What's the first thing?
So you're gonna draw a line from that point to the line of action of the force.
So in order to draw it to the line of action, I need to first draw the line of action. That's what I meant. You got it?
Oh, okay. Yeah. So
now what do? You said?
So I'm guessing you're gonna move up from that pivot point because it'll make a right angle with the
Is
line
that
of action.
correct?
Yeah.
This is correct?
No, I think you should angle it a little like to the left. There we go.
And that's the difference, right? So it's not just making this line go this way or this. It's like that's how you decide. It has to form a right angle. So that was that quiz question on the Canvas quiz that was so tricky. Remember that?
Yeah, and now it makes sense. Like, cause I
Yeah.
kept thinking like, oh, just make a line straight across, but no, it has to be a 90-degree angle.
It has to intersect.
Okay.
Yeah. And so that's why it has to be, in math terms, a perpendicular bisector. Cool. Because to be honest, this cuts the line in half. So does this, right? Because there's an infinite amount that way and an infinite amount this way. There's an infinite number of ways to cut this line in half because there's an infinite number of ways you could intersect the line of action. And since it's infinitely long, you always have infinite there and infinite here an infinity, there an infinity. All right.
And then you could just use like angle
Thanks,
rules,
Jesse.
like for perpendiculars, right?
Yeah, all the geometry of right angles and triangles and stuff applies. Yes. If I understood your question. Basically, once you now figuring out that distance, you're probably going to have to do trig or SOHCAHTOA or maybe Pythagorean theorem or et cetera, et cetera, et cetera. Got it?
Yeah, thank you.
All right. And you really don't learn lever arms until you do this chapter. So, because you kind of think, oh, you don't really need them in chapter 10 as much as you'd think. But in this chapter, we use them all the frickin' time. All right. So in case you're wondering why I showed you 4 methods to do it, some are good for coding. Some are good for this. Some are good for that. Blah, 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 blah. All right. Could have sworn that was a decaf, but now I'm getting frisky. All right. Let's get back to here. So that's a different one with cylindrical. Let's take a look at this next one. Let's see what we know in this problem. This is just the next problem. You have a nearly empty spool of wire. Looks like we know the mass. We know the radius. Oh, outer radius. We've got an inner radius. There is negligible friction wall. There's some. Oh, no zombies on this problem. We got a werewolf here. Hello. We got a werewolf pulling this spool. Oh, man. Zombies be damned. All right. All right. So we got some words there, a bunch of crap, whatever. I want to draw the forces. That's what helps us understand this, right? Oh, looks like I got a stupid little shadow on there. Sorry about that. Somebody tell me one force acting on this crap. Give me one force acting on the spool.
Tension.
Tension. Where does that apply?
That wire thing stick right there. You got to go up to the diagonal. That part, yes.
That's going to be the tension. It's actually on the inner radius because it said the spool was almost empty. Now that's kind of hard to see. Let me redraw that. And I'm going to draw this not to scale just so you can see the arrows. Sorry about that. Give me another force.
Normal force
From what to what or where?
from the wall going towards the center of the circle.
Okay, got it. Do we have friction upwards on the wall, downwards on the wall? What do you think?
Isn't it the friction is negligible?
Nice, good job. Okay, what else do we have here?
An mg going down from its center of mass.
All right, I like that one. Hold on. And then, okay, is that it?
There's a normal force from the bottom too, pointing up.
Aha, this one is not lifting off. Did you hear that in the problem statement? So in the original one, in the last problem, there was no normal force at the ground because we were told they're trying to lift off. In this one, there is a normal force. So I don't know which one I called 1 and 2, so apologies. I'll just call this one 1 and 2. I may have mislabeled those in the solution. I may have those switched. All that matters is that we draw this damn thing, right? Is there any friction or not at the bottom?
It's negligible, so right. Yes, there is actually.
Which way?
Is it pointing to hold on to the right?
Yeah, so if the zombie, excuse me, my bad. If the werewolf is pulling on this thing, the werewolf is trying to rotate it clockwise or counterclockwise?
Clockwise.
The werewolf's trying to rotate it this way. So that means the friction at the bottom must oppose that rotation. Oops, give me a sec. And go this way. Oh, you can't see that. So there's the friction at the bottom. Got it? What do you think of that FBD? Does that make sense? Or the forces on it anyways make sense?
Well, if the werewolf's pulling up, wouldn't it lift off of? Oh, I guess if it just keeps spinning in place.
What if the spool was made out of uranium? You could pull it and maybe cause it to twist. What if the spool was made out of uranium and it's sitting on ice? There would be a very, very, very small amount of friction. And as a result, you could imagine that it might actually spin but not lift off. Do you agree with that?
Yes, or it's
And-
basically like the spool's like emptying and just keeps going basically. So
Right. Now, in this case, the tension is going to slam it into the wall. Do you agree there's a component of tension trying to slam it into the wall?
correct.
And so that's why it doesn't slide. Whoops, wrong color. There's
Should be
this
like-
component of tension this way that's keeping it pressed against the wall. This one is trying to lift it up, but maybe the weight of this is so much that it can't lift up. And then again, I'm saying these vectors are not to scale. So that's the problem. I had to draw the tension really big just so you could see it. And so I could label it clearly. But this vector is not going to be bigger than the normal force either, but I had to draw it that way so I'd have room to label it. That's all. Cool with that?
That's cool.
All right. So, yeah. All right. Where is a good pivot point for this problem if you wanted to figure out the tension? Wait, did we know the tension? Sorry, I got to read the question again. Notice this is what I usually do with these problems. If I can tell it's a chapter 12 problem, immediately I'm drawing forces. Then I go read, right? So let me read the question now. The heck are we trying to do? Okay, what is the minimum tension required to make this thing spin? It says minimum tension to make it spin. What do you know?
About to slip.
About to slip. That tells us F1 in this problem is equal to mu static times the normal force. All right, so that's cool. How would you attack this problem? I want to get tension. What's a good point to choose as your pivot?
Well, since we need F1 and N1, I'd use N2 like there because you want to just get rid of the N2 and not have to use it.
Okay. Is there another point you could choose which eliminates N2?
You can choose the center, but then you get rid of MG and N1 and then N2. You get more. You get rid of more.
Which is good usually. The more you get rid of, the less you have to have in your equation. Here's the trick. If we choose this point, this force, and this force drop out. The normal force is still hidden inside right there. I don't know what that is. So that didn't get the whole problem done. We could do what Jesse suggested and redraw the torques about this point. That's bad because we'd have 4 torques to figure out. Do you see that?
I do, yeah.
And so that's not that you couldn't do it. Is there another way we could get information about this normal force?
And then she'd technically do F2 equals
The
U.
component of tension to the right is the same as a normal force too.
Something like that. You could write down sum of torques about the center, sum of forces in the X, sum of forces in the Y. That would give you 3 equations. You could figure out 3 things that are unknown. 1, 2. Ooh, oh, here's the 4th equation. This is a 4th equation, technically, right? So 1, 2, 3, 4 things. So once we know that, I would probably do sum of forces in the Y direction to get a relationship between the normal force and mg and use that. Now, granted, you could pick different torques. You could say, I don't know, you could pick this point over here that gets rid of N2, and maybe that would be a good spot, Jesse. That's basically equivalent to doing this and this. Got it?
Yeah, I got it.
Now, what is the torque due to the tension if I pick the center as the pivot? So I'm assuming I'm choosing the center as the pivot. What is the torque due to the tension? Just the magnitude would be fine. what method might you use?
Are perpendicular?
Okay. So is this, there's the line of action there. You want to try drawing the line of action for me? I don't know if you could figure out how to annotate on my screen, or you could just tell me what to do. You could tell me where it goes from what to what.
Going to be from the center of the thing to wait. To the center, correct? Don't you draw that next point? Let's see.
It's from the center to the line,
Perpendicular, correct?
which happens to be exactly where the force is applied. So this one, you could also just do RF sine theta. Agreed? Because theta is 90 and it's easy. What's this lever arm here? What's R perpendicular?
That should be, isn't that R thirds?
Yes, R over 3. And now that we have that, what's the lever arm for the frictional force? Somebody else. Gonzalo, you want to give it a go?
F1, right?
Yes. What's the lever arm for F1?
Okay, so let's do what we did for torque and make that line of action.
Got it?
And then we could just, okay, so we're using the center, right?
Yes.
Okay, so it's just gonna be kind of like MG going straight down.
Yep. So just cleaning up those other forces now, right? It would be
Yeah.
So what's that R perpendicular value in this problem? Is it R over 3?
I'm not sure, honestly.
Oh, it's just capital R. In this problem, they said the inner radius was R over 3. That's why R perpendicular was R over 3 for the tension. But in this one, the outer radius is capital R. That was all.
Oh, I see. I didn't have the book in front of me.
Yeah, I gotcha. All right. Okay. So what do you think of that, everybody? Does that make some sense? You take a problem that's really complicated and you can simplify it by choosing a pivot wisely. Notice the lever arms for circular things end up working out pretty easily. Let's see what else we got in here. See if there's something else on this problem I should mention. There it is. So make sure you understand this. And so I forget who it was. I think it might have been Jesse that was asking about, shouldn't this thing lift off? And I tried to draw this approximately to scale. The idea here is if we assume this coefficient of friction is about 1, these two arrows are about the same size. And then we see that there's some component up here plus some component up here, and those balance this down here. So it is possible to put this thing on the verge of slipping without lifting it up. And in fact, the more tension you apply, we know that the smaller this normal force gets because you're supporting more of the weight with the string. If you make the normal force smaller, the maximum possible value of friction goes down. And so it gets more and more likely to spin. And we expect that at some point, no matter what you do, this should spin before it lifts off. Because when this is a small but non-zero number, this horizontal component is going to be big and it will dwarf the maximum possible value and cause this thing to spin instead of lift off in general. What do you think? I don't know. I hope that made some sense.
Yeah, I just when I thought about like it's at the end of the reel, so it's like tied to it.
Oh, I see. It was close to the end, but yeah. I got you. I see what you're saying now. Okay. All right. Cool. And again, yeah, all that stuff. That if you were confused by that, that's the thing you could ask me about during the final or whatever. All right, here's a good one to do for you. Another good one. Here's a ladder one. We've got a couple of things I want to finish up with, and then I'll stop the live stream, give us a break, and then we'll come back and finish chapter 12. Okay. So give me just a little bit more here. I want to do as many of these circle problems. All of these ones that I've been showing you basically have been test questions, and they've all snowed people. So the reason I'm showing you this is because people have trouble figuring this stuff out. All right. For some reason, when you throw a circle in there instead of a rod, people get lost. And I think it comes from geometry. All right. So this one here, you got a sphere of mass m and radius r supported by a cable. Incline angle is alpha. This is shown at angle beta. Beta is this angle to the top of the incline. Okay. In this one, the cable extends radial away from the center of the ball. The lengths of the cable and the incline are not known. So the claim is, if you know alpha and beta, I claim you should be able to figure out gamma, this angle right here. How might you approach this? Anybody?
You draw the lines like going all the way through your pictures and try to
Okay.
figure out like, this geometry.
Yeah. Like that.
Yeah.
Notice we took a problem that had a bunch of non-right angles and we made two right triangles out of it. The big gray right triangle that alpha is in. What would you do next?
Move alpha. Oh, I put alpha up with that special thing because it looks like alpha equals, yeah, right there. Go up.
Right here?
Yep.
What do you
Since
say?
And then since that's 90 degrees, you can go alpha minus 90 for the top part for that triangle.
90 minus, but yeah, I got the idea. What else?
Can't you do the say like 90 minus alpha over alpha is equal to beta over gamma? Because they're both the same triangles. They're just or that does that rule not apply?
You said, say it again.
90 minus alpha over alpha is equal to beta over gamma, and then you just solve for gamma.
Beta over. So you're trying to use similar triangles, but they're not. I don't think that works. Because the big gray triangle, look at this. This is a totally different angle than that. Agreed?
Yeah.
So that wouldn't work.
Okay.
But I think another way I could see it is like, if you like looking at it closely, it's like two triangles adding up. Maybe there's like a geometry rule for that. I don't remember it.
And this is why this question killed people on the test. All right. And so we're learning the tricks of geometry. What's this angle right here?
180 minus alpha.
What's this angle here?
180
180
minus.
minus.
Then what?
You can split that in half.
Nope.
Perpendicular.
Nope.
You could do. Well, all those angles have to add up to 180, right?
Yes. The angles inside that triangle. So we see that gamma plus beta plus 180 minus alpha have to add up to 180 because they're all inside a triangle. The 180s drop. What's gamma?
Alpha minus beta.
And that's not necessarily what you were saying with your ratio thing. Do you agree?
Yeah.
All right. So we got that. Notice.
Yeah, that was that was the thing I was trying to remember. I forgot what it was called.
Oh, the triangle, the sum of the angles in a triangle. Okay, that's cool. Yeah, and I don't care about the name so much as the process. So if you got that, that's cool. All right. Now, generally speaking, we usually do one picture for getting a feeling for the angles and lengths. Then we do another picture with our forces. Okay. What's one force acting on this thing?
That'd be the
Tension.
force of the tension.
I heard mg. Where does that act? At the center, right? What's another force?
Tension.
Tension. Give me a sec. What's another force?
Normal force perpendicular.
to the curve
Yeah.
or to the
Perpendicular to the incline. Yep. Which way will that point?
Center of the sphere or circle.
Towards the center, right? Like that. Is there friction on this one?
No, it's negligible.
Sweet. All right. So there's our FBD. So, and just labeling these forces for a second. Okay. What are we trying to figure out in this problem?
Writing the forces and the torque.
Yep. And then in part E, eventually we try to figure out tension. What pivot point, if you were trying to determine the tension and you knew the weight of the ball, which pivot point would you choose for this problem?
Now, would you do the N one?
Yes. And so we see it takes a little experience, but you're starting to get it. Trying different pivot points can help you. You could have done the normal force or you could have done the center, but that takes out the only known quantity, mg. That's not a good idea. So in this particular problem, it makes sense to do the pivot point down there. So now, what do you think? What do you want to do? I'm going to draw the lines of action for these just in case we need them. Does this look like a good candidate for lever arms or not?
Not really.
I don't necessarily like lever arms for this one, right? So here's one. Now, maybe you could do it. The problem becomes, what's the lever arm for that tension? In particular, is it this? Is that the lever arm for tension?
No.
No.
Would it be towards the center of the circle?
Is that making a right angle?
No.
No. And see, this is the problem with this one. That. Oh, that's not even it. I'm having trouble. Oh, gosh, this is hard. About like that. Do you agree? So what the heck kind of angle is this inside of there? What is this angle that I'm trying to draw with multiple blue lines?
That'd be the Y. I forgot the name.
Gamma? I don't think so. If this is beta, this is 90 minus beta, which leaves beta for this. You see it? And so you could actually do the lever arm. This would be something like R cosine of beta, I think, is the lever arm for tension. And then for mg, what's this angle right here? This is tough, isn't it?
That one's gamma, isn't it?
Alpha. Take a look. Isn't that our same old FBD from chapter 5? That's why I was kind of chuckling. I've got you guys so turned around, you're having trouble with the chapter 5 problem. So when you look at this, if this is alpha, let's see, we could do this one here. This becomes 90 minus. That makes this alpha. That makes this 90 minus. I did that pretty quickly for Zoom. Let me do that again. I forget I'm on Zoom sometimes. This angle is alpha. That means the angle I just drew with the double bar and 2 dots and a smiley face, the smiley face angle equals 90 minus alpha. That means the frowny face angle that I just drew is alpha, which means the wavy face that I just drew is back to 90 minus alpha, which means quadruple bar is alpha. Got it?
See it now.
Woo!
Is that alternating angles?
I don't know. I don't care. Yeah, it's some kind of rule. How about that? It's some kind of rule.
I'll just look it up.
Yeah, I don't know the names of that crap anymore. I was pretty good at geometry. I'm still all right at it. But I tell honest, I should learn those names. I just don't know that stuff. It's not something I care about at all.
So instead of doing leverage arms, what would you do? Just the RF?
I don't know. I guess we basically just did the lever arms. Do you agree? Or
Yeah.
or you could do RF sine theta. Which problem was this one?
12.18.
So you could do lever arms. Oh, it looks like what I did for this one was I just said it's R mg sine alpha. So I did RF sine alpha, whereas I did a lever arm for the tension. So we actually did that one pretty similar to how I drew this one. Notice I had to draw really big pictures. If it makes you feel any better, I wrote this problem. I wrote this solution. And earlier today, I accidentally called alpha gamma. So I have trouble with these too. You have to be patient and work your way through it rather than guess at it. And so this is about as hard as I could imagine this one. Ironically, I discovered after I gave this question on the test, some people were able to solve this problem with just forces. And it actually works out. The issue was I did not see this. The test, everybody was turning in answers that looked like this. Turns out these are all equivalent ways of writing the answer. And when I first marked everybody down, they're like, that should be right. So I had to go back. It's crazy. Yeah. There you go. Got it, Gonzalo. But so any of these answers ended up being full credit on the test. You can see there's lots of different ways to write the correct answer. So it's a nightmare to grade this kind of problem. Well, what do you mean they wrote it down verbatim like that in the workbook?
Like they did T equals blah, 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 equals blah, blah, blah.
Some people did it like this. I think somebody did it like that. I think somebody else did it like this. Somebody did it like that. And so each person solved it differently because some people use torque, some people use forces, and everybody had done their angles in a different way, just like we were just talking. And so eventually I figured out all the different possible correct answers and gave everybody full credit, but it took a while. So all those times that I make you work your ass off, these problems end up being a lot of work for me too. So you can say it's karmic payback for trying to make you guys work so hard. All right. Oh my gosh. I wanted to get to a break. Oh my gosh. Let me, let's get class done early and let you out early instead. Sound good? And what I'll do is I'll give you the last 20 minutes. Let's keep going and just get this done. All right. Okay. So I've shown you all the possible tricks I could think of with these circles, all the possible tricks I had with rods. There's a couple more things I want to talk about. Number one, tipping over. I'm going to look at this. Two more things, and then we'll be done, I think. Let's say we want to talk about tipping over. This is a pretty interesting problem because up till now we've talked about things slipping, but not tipping. Let me get over there. All right. So imagine we have this situation. You're raising this platform up and up and up. It's going to tip over at some point. Which point acts like the pivot point if it's tipping?
Should be the bottom of the corner.
This is going to be the pivot point. Now, I happen to draw this thing at just the right spot so you could see it, I hope. Which way does gravity point?
Down.
Straight down.
Yeah. And now I'm going to cheat and draw the line of action with the line here.
Is that dot the center of mass of the?
Yes, that's the center of mass of this block. So let's say I ordered something from Amazon, and for some reason it had a high center of mass. So it's sitting inside the box, and the center of mass doesn't have to be in the center of the box. Do you agree? If you ordered like a weight set or something, and one of the weights was off center, that could shift the center of mass. Are you okay with that? Or maybe I took a box and flipped it upside down, and so the low center of mass. Maybe this was a coffee maker I ordered from Amazon, and the coffee maker has a heavy base, but then I put the box on the tray upside down, so now the heavy base is close to the top of the box. Are you good with that, Alonzo?
Yeah, makes sense.
All right. So this red line is supposed to be the line of action. If that's the line of action, do you agree there is a very, very, very small lever arm going this way? Whoops. Oh, that's not right. I can't draw it with that. There's a tiny lever arm. And now Jesse's never going to see that. Nobody's going to see that. All right. The point is there's a tiny lever arm there to the left. Okay. So to be clear, if I could exaggerate this a little bit, there's a tiny lever arm this direction, R perpendicular. As soon as the line of action for the center of mass moves past this pivot point down here, you get a tiny lever arm, and there's a torque this way, and the thing tips over. So if you're wondering about things tipping over, look at their center of mass. Look at the pivot point, which is some corner of the box or whatever. And then if the line of action for the weight goes outside the object before you get to the tipping corner, the thing's going to tip over. Whereas if you do this again at a lower height, just give me a second. If the center mass was lower, let's say the center mass was really low. Here's the pivot point. The line of action is over here. The lever arm is this way. mg is down here. There's actually a torque rotating it that way, which keeps it from twisting. Obviously, that torque is balanced by a normal force producing a torque that causes it to rotate the other way, and those two balance out, causing no net rotation. Question?
So no matter how small the lever arm is, once it crosses that line, the box is gonna rotate.
Yeah. What kind of objects tip over? Short, fat ones or tall, skinny ones?
Tall, skinny ones.
Yeah. Let's take a look at this one. Let's say I take a plank like this and I put it on an incline. You know from experience, this plank has its mg at its center. This is way past the tipping point. The lever arm is right here, R perpendicular. You're clearly going to get a torque from the weight that's going this way, and this thing's going to tip over. That's why tall, skinny objects tip over, because their center of mass is so high up in the air compared to the aspect ratio of the object. You're always going to get this lever arm producing a torque, causing it to tip over. You good with that?
Yeah, so no matter like the weight or
that's right. This would tip over if it's a tall, skinny piece of foam or if it's a tall, skinny piece of lead.
As long as the center of mass passes the pivot point.
Yeah. Whereas think about a textbook. A textbook is long and skinny this way. You put that on the ramp. The center mass is right here. mg is right here. The pivot point is right here. There's no way a textbook is going to tip. It's going to slip. Notice the lever arm goes the other direction relative to the pivot point. So mg causes a torque that keeps this thing. Have you noticed how many times today we've said the words lever arm? It's pretty convenient for understanding torques, isn't it? All right. Is everybody good on tipping? I hope so. One more, and then we're done, okay? Now, these ladder problems are cool. Imagine you're a civil engineer. You could imagine this type of problem where you have a tie rod. That's what this thing is. You guys could study that later. That's a foreshadowing of the class statics. But that's not the one I want to look at. It's a cool one, though. Whoops. I want to look at this one. The one time we actually use fictitious forces. So before we do this one, let me work this out on the board. Okay. Hang in there, people. Appreciate the stamina you guys are showing tonight. Appreciate the hard work, okay? Take a look at this. I've got a block here. Let's say there's a force this way, there's a normal force this way, and there's mg. Let's just say these are the forces. I hope you agree this thing would accelerate to the right. Right? And then, so if I wrote the equations for this in the x direction, I would get F equals mass times acceleration. And actually, I'm going to write the MA in red. All right. Now, what I could do is I could also move this to the other side like this. Let me do it like this. Sorry. Force minus MA is equal to 0. Same equation, just rearranging it. Aha. But isn't that the same thing as drawing this picture? What I've done is I've created a force going to the left that happens to be this size. If I identify this as force fictitious and then say there's no acceleration at all, the math works out. So this equation down here, if I assume there's a force to the left and no acceleration, mathematically, I get exactly the same result as if it's going to the right and it's accelerating. Now, this pisses everybody off because it's weird, uncomfortable, and full of lies, right? Because this is just not happening. It's fictitious. That's why the name is fictitious. However, mathematically, there's a huge benefit, and I'm going to show you, right? This is called fictitious forces. We talked about it in chapter 6, and I said we only use this once in chapter 12. This is chapter 12. This is the problem. Okay. Where'd it go? You got a car. You're driving in a circle. What is one force acting on the car?
Friction.
For the center.
Okay, friction towards the center. What? Okay, what else?
AC?
Gravity.
Gravity. I'm going to start with gravity because that's an easy one. All right. Let's assume the center of mass of the car is right there. Gravity should act downwards at the center of mass. Now remember, this is not a car driving in a straight line. There's a center of the turn over here. Which way is this thing accelerating?
Into the page.
Towards the center of the turn. AC. It's moving in or out of the page. The velocity points out of the page. For example, looks like the car's about to run into my face and smash me. All right. So humor me. Let's pretend this AC doesn't exist by changing it into a fictitious force. The fictitious force must point the opposite way. I'm going to call this force fictitious, which happens to have the same size as MAC. Okay? By definition, the acceleration of the center mass should be to the left. So that means it's equivalent to a fictitious force going the other way. And if I do this, that tells me that acceleration is 0. Now, based off this picture right now, which way is this car going to tip if you had to guess? If I go too fast, is it going to tip towards the middle of the turn or towards the outside of the turn based off what you see?
Outside.
Outside. So as it's about to tip over, which wheel remains in contact with the road?
The right one. Going with the person will be the left, but yeah, that one.
Yeah, whatever. Yeah. So there's a normal force here and a friction there. So, right. And now we could treat this as a statics problem because we set A equal to 0 by using this fictitious force trick. What's the obvious choice of pivot?
The bottom right corner.
And now I could see this is going to have an MAC in it, which is mv squared over r. I could figure out the maximum speed to drive before you tip. Sucker! What do you think of that? Isn't that cool? I think that's cool. I have a strange vision of what cool is. Okay. So I'm going to stop the live stream. Yeah, exactly. So, well, I will say this. Those problems are cool. And I think, what was that, 16 and 19? I'm going to be straight with you. I'm not putting something like 16 or 19 on the final exam. But I do think you can learn from them. Enough said, right? So I hope you learned from them just what we did right now. So if you want to know how fast you could drive before tipping over, or if you want to learn about tipping over, or if in a future class that's important, just kind of put that in the back of your mind that we did cover it and that you could go back and read this later if you need it. All right. I'm going to stop the live stream there.